In December 2022, when Artemis 1 splashed down in the Pacific Ocean, the engineers cheered. Then they looked at the heat shield. The ablative material, the outer layer designed to char, flake, and burn away in a controlled pattern, had eroded in ways the thermal simulations had never predicted. The underlying structure held, but the damage was serious enough that NASA convened an independent review team. Some engineers said no. They argued for a redesigned shield before any human being sat on top of it. And quietly, almost without announcement, the emergency survival plan that kept the Apollo 13 crew alive after their spacecraft exploded became the primary flight plan for Artemis 2. NASA gave the go-ahead anyway, and on April 19, 2025, 4 astronauts climbed into that capsule. Tonight, those 4 people are closer to the moon than any human being has been in over 53 years. They have already seen things no human has ever seen. And in approximately 40 hours, they will face a re-entry at 25,000 miles per hour, faster than any crewed spacecraft in history, behind a heat shield that the data said should not have flown. This is not a story about a mission going well. This is a story about what happens when you launch anyway. Start with what Apollo actually was. Not the mythology, not the moonwalk photographs. Apollo was a controlled emergency, 12 years from a standing start to the lunar surface, driven by the fear of Soviet dominance. At peak, the program consumed approximately 4.5% of the entire federal budget, equivalent today to roughly $280 billion a year. That kind of money buys speed. It does not buy elegance. The Apollo command module gave 3 people about 210 cubic feet of space, the interior of a large closet, 3 grown men, a closet, up to 14 days. There was no toilet, there was no privacy. There were plastic bags, adhesive bags taped to the body, used in front of each other, then sealed and stored inside the cabin for the rest of the mission. Nearly every Apollo astronaut who spoke candidly about it called it one of the worst parts of spaceflight. There was no exercise equipment. NASA calculated that on missions under 2 weeks, the muscle and bone loss was acceptable. The crews came home weak. Some could barely stand. The computers had 72 kilobytes of memory and could execute around 40,000 instructions per second. A modern digital wristwatch outperforms them. The cockpit was analog switches, physical gauges read by hand. Mission Control in Houston made most of the critical decisions. Apollo worked because it threw extraordinary resources at a narrow problem: get Americans to the moon before the Soviets and bring them home. It solved that problem. It solved nothing beyond it. When Apollo 17 left the lunar surface in December 1972, no human being returned to deep space for 53 years. Not because the technology failed, because the political will did. What replaced it took half a century to build, and it is a fundamentally different kind of machine. The Orion capsule gives 4 people 330 cubic feet of habitable space, nearly 60% more than Apollo. There is a hygiene bay with actual doors that close. There is a toilet, the Universal Waste Management System, nearly identical to the one aboard the International Space Station, that collects waste separately, processes it, and provides something Apollo never offered: privacy. The exercise equipment is a flywheel device weighing 30 pounds, the size of a carry-on suitcase. A cable mechanism delivers up to 400 pounds of resistance. The Artemis 2 crew can row, squat, and deadlift. For comparison, the exercise equipment aboard the International Space Station weighs over 4,000 pounds and occupies 850 cubic feet. The flywheel does a significant fraction of the same work in a fraction of the mass. The Artemis II crew will come home having done deadlifts in zero gravity on the way to the moon. That sentence would have sounded completely absurd to anyone alive during Apollo. The Space Launch System generates 8.8 million pounds of thrust at liftoff, 17% more than the Saturn V. Both rockets fly once and are gone, but what sits on top is not the same. Apollo ran entirely on fuel cells. Hydrogen and oxygen combine to produce electricity, and as a byproduct, drinking water. Elegant, finite. Every watt the crew used came from a tank getting emptier. Orion unfurls 4 solar array wings after reaching space. Photovoltaic cells convert sunlight into electricity. As long as the sun is shining, the power supply is for all practical purposes unlimited. This changes the psychology of the mission in ways that are easy to underestimate. Apollo crews were always managing the clock, oxygen depleting, power running down, water rationed. Orion's crew still manages consumables, but the electrical margin is different. Systems can run longer, harder, with more redundancy. The spacecraft does not feel like something counting down to zero. And then there is the service module, the section of the spacecraft providing propulsion, thermal control, and life support. It was not built in the United States. It was built by Airbus Defence and Space in Europe, provided by the European Space Agency. Apollo was an American project from the rivets up. Artemis is international by design. A Canadian astronaut is on this flight because of a treaty signed in 2020. European hardware is keeping the crew alive. The era of one nation going to the moon alone ended in 1972. Subscribe to Deep Horizon Space and hit the notification bell so you never miss a mission. Now look at what is behind the panels. Orion's flight computers are approximately 20,000 times faster than Apollo's guidance computer. Apollo's guidance computer had 72 kilobytes of memory total and could execute around 40,000 instructions per second. A modern digital wristwatch embarrasses it. Orion runs 4 independent computers in parallel, each one roughly 25 times faster than the computers aboard the International Space Station and 400 times faster than the space shuttles. The cockpit is entirely digital. Glass screens, software interfaces, real-time trajectory adjustments. Apollo's cockpit was analog switches, physical gauges read by hand. Mission Control in Houston made most of the critical decisions. Orion can fly itself. It demonstrated that on Artemis 1 in 2022, the uncrewed spacecraft completed a full lunar mission and returned to Earth autonomously, without human input. The Artemis II crew has been performing manual piloting demonstrations in deep space, physically flying the spacecraft, testing different steering modes, evaluating how the vehicle responds when a human is actively directing it. The Apollo astronauts flew manually during docking and landing. They never flew the command module through open space the way this crew just did. And on day 4 of the mission, the crew pointed cameras toward a feature of the moon that sits on the transition zone between the near side and the far side. The Oriental Basin, a massive impact crater roughly 600 miles across. Robotic spacecraft have mapped it, but the Apollo missions were planned so that this region was always in shadow or just outside the line of sight. No human being had ever seen it directly. The Artemis II trajectory changed that. For the first time in history, 4 people looked at a feature of the moon that only machines had seen before. And they transmitted those images back to Earth using laser communication, infrared light carrying data at rates that would have been unthinkable during Apollo. By day 4 of the mission, The system had already downlinked 100 gigabytes of high-resolution imagery. Apollo's total data returned from an entire mission measured in megabytes. The Artemis 2 crew is streaming the moon in near real time. Apollo sent sketches. This crew is sending the painting. Now we come to the part that the mission briefings describe in careful language. When Artemis 1 returned in December 2022, the heat shield appeared intact. The capsule had survived re-entry at high speed. The mission was declared a success. Then, the post-flight analysis began. Engineers found unexpected erosion in the ablative material. The outer layer of the heat shield designed to char, flake, and burn away in a controlled pattern, absorbing heat through its own destruction. Portions had eroded in ways the thermal models had not predicted. The erosion was uneven. The pattern of degradation did not match anything the simulations had generated. The heat shield was not failing in the way engineers expected it to fail. It was failing in a way they did not understand. NASA convened an independent review team. The investigation took years. Some engineers wanted a redesigned shield before any human being sat on top of it. Some wanted to delay the program. The debate inside the agency was serious enough to become public. Now, remember the emergency plan that saved Apollo 13. In April 1970, an oxygen tank exploded inside Apollo 13's service module. The mission was over. The question became survival. The crew executed what is called a free return trajectory, a path that uses the moon's gravity to arc the spacecraft back toward Earth without requiring a major engine burn. It worked. The crew survived. The free return trajectory was an emergency measure, a last resort. Artemis 2's primary flight plan is a free return trajectory. What was once an improvised survival procedure to bring a dying crew home is now the standard architecture for the first crewed lunar mission in 53 years. NASA Administrator Jared Isaacman reviewed the heat shield data. He met with engineers, with outside experts, with the independent review team, and he gave the go-ahead. The shield flying on Artemis 2 is essentially the same design as the one that showed unexpected erosion on the uncrewed test flight. A redesigned shield is planned for Artemis 3. The crew knows this. They accepted the risk. This is not negligence. This is the logic of exploration, the acknowledgement that the engineering is not perfect, that the margins are real, but not infinite, and that if you wait for certainty, you wait forever. When Orion hits Earth's atmosphere on the return, it will be traveling at approximately 25,000 miles per hour. Faster than Apollo, faster than the shuttle, faster than any crewed spacecraft has ever traveled during re-entry. The heat will approach 5,000 degrees Fahrenheit as superheated plasma wraps around the vehicle and blocks all radio communication. For those minutes, the crew will be completely alone, unable to talk to Houston, unable to receive data, unable to do anything except trust the engineering. The same engineering that produced unexpected results last time, behind a shield that some engineers argued should have been redesigned. That is the bargain. That has always been the bargain. The crew itself represents something Apollo never did. Victor Glover is the first person of color to travel beyond low Earth orbit. Christina Koch is the first woman. Jeremy Hansen is the first non-American citizen, Canadian, selected through a 2020 treaty formalizing Canadian participation in the Artemis program. Apollo was exclusively American, exclusively white, exclusively male. Not because NASA explicitly excluded anyone, but because the pipeline that produced military test pilots in the 1960s was itself exclusionary. Artemis II does not fix that history. Nothing can. But the first humans to see the moon up close in over 50 years look more like the species they represent. And inside the cabin, a quieter experiment is underway. The crew is being monitored for the biological effects of deep space radiation in ways that go far beyond anything Apollo tracked. Radiation dosimeters, sleep pattern analysis, cardiovascular data, all of it recorded to understand what 10 days outside Earth's magnetic field does to the human body. In low Earth orbit, Earth's magnetic field deflects most dangerous charged particles, trapping them in concentrated bands called the Van Allen belts. Every crewed mission since Apollo 17 has stayed safely below those bands. The Artemis II crew punched through both belts on the way out and will punch through them again on the way home, exposed to the very radiation those bands concentrate. Apollo astronauts reported seeing flashes of light with their eyes closed, cosmic rays striking their retinas. We know more about what causes those flashes now. We know the risks are real, cumulative, and incompletely understood. The data from this mission will shape every deep space crew selection protocol and mission duration limit for decades to come. Because this mission is not really about the moon. Orion has already been evaluated for a 1,000-day mission profile when paired with additional habitation modules. The life support they are validating, the navigation they are testing, the heat shield they are trusting, the radiation data they are collecting, all of it is being designed for a mission that comes after this one. Apollo proved we could leave. Artemis is figuring out how to stay gone. Tomorrow, they fly behind the moon. For approximately 40 minutes, Orion will pass through a zone where the lunar mass blocks all communication with Earth. No signal will reach them. No voice from Houston. No data link. No connection to anything human except the 3 other people floating beside them in a capsule 250,000 miles from home. The Apollo astronauts knew that silence too. Every crew that flew to the moon passed through it. It is the one experience that has not changed. The technology has transformed almost beyond recognition. The computers are 20,000 times faster. The cameras transmit 100 gigabytes in 4 days. The spacecraft can fly itself. The toilet has a door. And yet, for 40 minutes, 4 human beings float in a metal capsule with no signal, no contact, no safety net. The moon still blocks the signal. The void is still the void. When they return, the data they bring back, including what that heat shield looks like after a 25,000 mile/hour re-entry, will determine whether Artemis 3 launches on schedule, whether the redesigned shield flies, whether humans walk on the moon for the first time since 1972. Some engineers said no to this mission. They were right to flag it. The data from Artemis 1 was genuinely alarming, and the people who argued for a redesigned shield before a crewed flight were not being cautious. They were being correct. The crew went anyway. That is not recklessness. That is exploration, the deliberate decision to move forward under incomplete information, because staying still is also a choice, and it carries its own risks. The Artemis II crew will splash down in the Pacific sometime around April 11th. Recovery ships will be waiting. Divers will approach the capsule and help 4 people climb out into the sunlight. Those 4 people will have tested every system that future crews depend on to land on the moon. They will have seen the Oriental Basin. They will have done deadlifts in zero gravity. They will have traveled farther from Earth than any human who came before them. And they will have trusted an imperfect heat shield, not because the risk was acceptable, but because the alternative was waiting for certainty that never comes. 252,757 miles from Earth, 4,100 miles beyond Apollo 13's record, set not by disaster, but by design. The silence behind the moon is the same as it was in 1969. Everything else is new,